All right, thanks, Deborah. Yeah, it's really great to be back. It's been a long time since I've had a chance to give a talk at MIT. And one thing I remembered from organizing the LIDS colloquium was that we strategically put the seminar at the end of the day. And that was like, it's like you're running the seminar speaker through the gauntlet during the day. This is the most endurance testing approach to seminar design, right? I really appreciated that. It was great meeting a bunch of people during the day. I had a lot of fun. I do think LIDS is just in an incredibly exciting place. So it's really fun to see all the stuff that's going on here. So yeah, I'm very excited to tell you about this work. Since we're starting a little bit late, I'm just going to jump right in. The talk is about experimentation in marketplaces. One thing I should say, though, is it's joint work with Hannah Lee, who was a postdoc here, some of you may have met, a current PhD student, Anushka Murthy, who's in MS&E in my department, and then Gabriel Weintraub, who's at the GSB, although as of Thursday has just left Stanford and is moving to Chile. So he's a longtime collaborator of mine. Okay, so the talk is about experimentation really under inventory constraints. And the specific example I'll keep referring to just in terms of the language I use when I deliver the talk is inventory constraints in the context of marketplaces, where guests, for example, may arrive to a site like Airbnb and be looking to book listings, but there's a limited inventory of listings. But I just want to point out a couple of other sort of types of things I've worked on where I think similar issues arise. One is in the context of healthcare clinics, where you have many patients, few providers. So those patients interact with sort of a capacity-constrained system that's where care is mediated through a small number of providers. Another one, an ongoing collaboration with Netflix that's related to congestion that occurs at exit from their data centers. Netflix serves, depending on what part of the country or the world you're in, somewhere on the order of a quarter of the bits on the internet at various times. And so there actually is real congestion in the exits from their data centers where you have competition between the same streams. So if you randomize viewers in an experiment, they're actually competing with each other for scarce resources. So again, like I said, I'll use the language of marketplaces to talk about capacity constraints, but I don't want you to sort of over-index on marketplaces. I think I'm going to try to abstract from that a little bit. Okay, so what is the talk about? So the talk is about the fact that marketplaces will commonly use experiments to assess the value of interventions. And so typically we refer to these things as A/B tests because the tech industry has a new name for everything. So A/B tests are just randomized controlled experiments. In two-sided marketplace platforms, you might ask questions like, what's the impact of changing the checkout flow? What's the impact of changing the amount of information I provide? What's the impact of changing other aspects of the market design? In all of these cases, what you're typically asking yourself is, what do you think would happen if you rolled the intervention out to the whole market versus you didn't roll the intervention out to the whole market? So that difference, the difference between the entire system in treatment versus the entire system in control, is what's called the global treatment effect, or the global average treatment effect. And that's what's called the estimand of interest, the target quantity of interest. And so we're running experiments to try to estimate this quantity when we have a new intervention. So something that's been well studied at this point, I've got a small caricature you may have seen before actually, because these are Hannah's slides. These first few slides date back to Hannah's job talk. Something that's been well studied up to this point is the fact that because there's a common inventory of listings, you have statistical interference that's created if you pursue standard estimation techniques in this setting. So let me just make that more concrete because it's a bit of a vague statement. So imagine a world in which I have a set of listings and just two customers in the world, a highly caricatured world. And I'm testing a new feature that makes treatment listings more attractive. Okay? So I'll represent that sort of by the idea that these are more attractive, less attractive. In global treatment, I want to estimate what would have happened if everybody was seeing more attractive listings. Global control, everybody is seeing the vanilla plain listings. Okay, this might be something like more attractive profile pictures for the listings or something like that. So if I randomize customers to treatment and control, just to keep it simple, imagine this customer is in treatment, this one's in control. There's only two customers. Randomization is pretty simple here. So let's imagine this customer, they'll see the world as if it's in control. The two listings they're considering are these two. They see them as if they're in control. This customer is in treatment. They'll see these two listings as if they're in treatment. Okay, that's what randomization means. Now, you can see kind of that in a world in which the treatment customer arrives before the control customer, for example, the booking outcome of the treatment customer has a direct impact now on what happens to the control customer. So, for example, if the treatment customer is more likely to book, maybe they book this middle listing, but then that reduces supply to the control customer, which is the textbook definition of interference, because now the treatment status of one customer is impacting the outcome of another customer. Okay? In this case in particular, you can actually go a bit further than that. And one thing you can see is that the treatment customers are seeing a relatively less competitive market in the experiment than they would see in global treatment, because they're seeing fewer customers that are more likely to book than they would in global treatment. And the converse is true for the global control folks. In global control, the market is more, sorry, I think I said this backwards. This is a more competitive market than this one for the treatment customers. This is a less competitive market than this one for the control customers. And because of those effects, you actually overestimate the treatment effect. Okay? You overestimate the rate at which the treatment customers book. You underestimate the rate at which they would book relative to the respective globals.
But don't you run this like A/B testing on a very small subset of the population? So it shouldn't matter. Like basically, this interference effect is very small.
Yeah, that's a good question. For the purposes of what I'm talking about here, you should certainly be thinking about situations where A/B tests are being run at scale. Even when they're run in small populations, usually they're run in small populations that are subsets where interference is a problem. So it's, for example, there are some tests that are run at 10% at global scale, for example. So maybe that's a place where, yeah, that's legitimate. The kinds of things I'm imagining are something where, yeah, I'm running at 10%, but 10% is within a cluster. Like New Zealand is often highlighted as like a textbook country that we experiment on before we roll things out to the entire world. There's like old articles written about Facebook experiments in New Zealand for this reason. I think that's a legitimate point, though. I mean, one thing I like about this space is that there's lots of degrees of freedom, and so pretty much everything that you guys will ask me is going to be something that I don't have a great answer to. I haven't thought about thoroughly. Yeah. Okay, so. I'm not going to spend a lot of time rehashing related work on bias. The main thing I'll say is that most of the emphasis of existing work on this topic has been on sort of focusing on either quantifying the bias that's created or doing something about it. Okay, so that would range like, sort of how large is that bias, but also what are alternative experiment designs I could use, alternative estimators, or both together that I could use to do something about this bias. Maybe the point of this talk is actually somewhat different, and it came from a very concrete issue that arose when I tried talking about this work with, this work was the initial work that Hannah and I and Gabriel did was together with the data scientist at Airbnb. And one of the things that came up when we were then sort of presenting these results more broadly there and elsewhere is that people were asking the following question. Well, you're showing me this caricature where the treatment effect is overestimated. Is that bad? Because if the treatment effect is overestimated, I'm not getting the sign wrong. And if I'm not getting the sign wrong and I kind of care about launching this thing, is that really that big of a deal? And I thought that was a really good question. Like, it's a very simple but compelling question. And I should have a good answer to that question, which we didn't at the time. And that was really the departure point for this work. I mean, one of the things that prompted me to think about was just, how would I answer the question, does interference matter if I want to make a decision? So that's the title of the paper and the talk. And that's really what we'll focus on today. The main takeaway, and I want to qualify this a little bit. I'll try to tell you where the qualifications around this claim are. But one takeaway is that for a wide range of treatments, interference can actually be beneficial. And you want to, I think if you hear that type of comment on a slide, you want to take that in with the right grain of salt. So I'm not claiming that this, first of all, I mean, just as a basic thing, I'm not necessarily claiming this undermines my own research in the area, okay, so that's important. And I'm also just not, I don't think I'm claiming that work that we do on interference and debiasing and alternative designs is a dead end as a result. That's not really the point. I think for me, actually, the more compelling takeaway is that this kind of work makes it pretty clear to me that you want to be pretty thoughtful about exactly when you invest the effort into a debiasing design or estimator. And I hadn't really appreciated that sort of distinction before. And so that I think is where I'm hoping there's something compelling. Besides that, I just found sort of the methodological aspects of some of this work kind of interesting to do. So hopefully that'll come through. Okay, So brief outline, the rough way we're going to follow this is we're going to build a queuing model that represents a caricature of the platform, and we'll use the queuing model and instantiate 3 different ways: for treatment, for control, and for an experiment, and then we'll do everything else in that world. Okay, so I'll tell you kind of decision making will follow frequentist hypothesis testing, and then I'll talk to you about sort of the implications. All right, so what's the model? Essentially, as I just said, we'll think about 2 different inventory-constrained systems as treatment and control, and experimentation is going to be a mixture of these 2 in a way that I'll make precise in a second. Similar models studied in a range of different papers. I put H and S here because these are 2 different Lees. So this is Hannah Lee, who I already mentioned, and then this is Shuangning Lee. So all of these papers in different ways use sort of these kind of stateful queuing models underneath models of experimentation. I hope people here are familiar with this pair of papers by Vivek Farias, Tianyi Peng, Andy Zheng, and a few others. Really, really nice work that I think starts connecting the dots over to reinforcement learning. And I think that's a very good sort of toolbox for us to be thinking about with these kinds of problems. Okay, inventory dynamics. I'll summarize quickly by saying that the inventory dynamics are a birth-death chain. And the only reason these slides exist is to give a little bit of notation to that birth-death chain. Okay? So what's the birth-death queuing model? Customers arrive over time. They can book listings if one is available. So crucially, it's a birth-death chain with a finite buffer, finite inventory of listings available. The state over time will be the number of booked listings of this chain. Customers they arrive as a Poisson process. Now, one thing we do allow in the base model is that customers can be heterogeneous. And I want to point out here, this is heterogeneity that's sort of irrelevant from a math standpoint, because I can, I better not do that, that I can aggregate Poisson processes, I still have a Poisson process. That's not interesting. The reason to include the heterogeneity explicitly is just as a modeling point, that heterogeneity among customers that's unobservable to the platform is allowed as a matter of like the conclusion that I'm drawing. One thing that's not part of the model a priori is listing heterogeneity, and I'll return to that. Hopefully I'll have a minute to spend on that at the end of the talk before I wrap up, okay? Now the overall arrival rate is denoted lambda, which is just a sum over these different types. And then, like I said, I have a fixed capacity of listings, k listings, and that's the total inventory. And so what's happening over time is customers book listings, which means the available inventory at any given time is less than k. It fluctuates over time. That's the birth-death chain. Right? I make kind of a few other primitives that I need are just how do I book and how do listings become available. Because I have a birth-death chain, I need birth rates and death rates. So where do those come from? So the birth rate comes from a booking probability of arriving customers. So this is the probability that an arriving customer books when there's k minus k listings available, or equivalently little k listings already booked. And I'd expect that to be decreasing in the number of available listings. Okay? That kind of admits almost every model of interest to us probably is going to look something like that. And lambda of k is just the aggregation of that net booking rate over customers. So customers arrive, they book, and then, as you can see, like if you think about the thing I said at the beginning of the talk, because customers arrive and book, that changes the state of the system as seen by subsequent customers. So this is in some sense like the simplest model in which you can easily see the intertemporal interference effect that was outlined at the beginning in that like toy model, right? Simplest stochastic model. Okay, and then the other thing I need is like a rate at which listings become available again. So that for when k listings are booked, that'll be tau of k. And the only thing I assume about this is that this is also non-decreasing in k. Like one simple example would be if every listing is held for an independent exponential time before becoming available, then the tau rate would just be constant times the number of booked listings. Okay? But you could have an MM1 type model where it's a constant death rate over time as well. Okay. So number of booked listings with this kind of definition then becomes a continuous time birth-death chain. Okay. Up to this point, I'm not saying anything very deep, I hope. If LIDS education today looks anything like it did when I was here, that should all be standard for folks that are in the room, I hope. Like the simplest Markov chain that you would see. Okay. What's that?
That's a dangerous.
Oh, no, don't tell me that. Don't tell me that. All right, let me pause for a second. So have I said anything that anyone wants to ask questions about? Especially after saying that, nobody's going to raise their hand. So let me summarize the model so I don't put anyone on the spot, all right? So the model is, I have a Markov chain whose state is the number of booked listings. This state moves up when a customer arrives and books. Okay? So one subtlety you have to keep in mind, I think that'll be important when we define the data, is that I get to observe all arrivals. And the data will be the booking outcome of customers, which is 0 or 1. So that's one sense in which it's different than a classical birth-death data model, because I'm also getting data from customers that don't book, that don't change the state of the system. Okay? But other than that, the state changes if customers arrive and book. That reduces the number of booked listings, increases the number of booked listings. And then the number of booked listings goes down by 1 every time a listing becomes available again. The rates of that happening are lambda of k and tau of k. That's the model.
And what is the treatment?
Okay, good. So I'm getting there. Haven't gotten there yet. So right now, this would be like 2 instantiations for treatment and control. The treatment is going to be on the booking probabilities. Okay? So what I'm imagining is that I have 2 different systems that change the booking probabilities. And I'm going to use subscript 1 and 0 to denote treatment and control. Lambda 1 of k is the booking rate in state k in the treatment system. Lambda 0 of k is the booking rate is the arrival rate in the control system. So if I normalize by lambda, then these are the steady state average booking probabilities. And kind of the interesting thing from an interference standpoint to see sort of as a matter of algebra is that treatment changes 2 things. There's the direct effect of changing the rate and the indirect effect of changing the steady state distribution. And so the question really from an inference perspective is, can I estimate both of those 2 things together? Estimating the direct effect is usually the easy thing. The hard thing is estimating the indirect effect. Okay. All right. So 2 slides of data randomization and estimation that are, I think you'll only need to track the notation on these couple of slides. So we run an experiment with n arriving customers that are Bernoulli randomized to treatment or control. So y is the booking outcome of the ith customer. And the treatment assignment of a customer, Bernoulli randomized. N1, N0 I'll use to denote the number of customers in treatment or control. Okay? All right. Any questions on any of that notation? Does that make sense? So first n customers that show up, I'm going to just Bernoulli randomize them over time and then allocate them. Now, notice that what's happening here is that means that the effective system created in the experiment is a mixture of the 2 birth-death chains, because the booking rates will be dependent on whether I got randomized into treatment or control. Hopefully that's clear. All right. So estimators, the estimator of interest to us in this talk is going to be not an interesting estimator. It's the difference in means estimator. So we just literally take the average booking in treatment, average booking in control, and the difference of the 2. The associated variance estimator, that's the typical thing you learn in Stats 101, is just this like pooled variance here where I've got the sample variance in the treatment group, sample variance in the control group, normalized by the sample sizes. And I think I want to point a couple things out on this slide. First of all, why focus on this? This is by far the most common way that people form estimates in industry. Okay? And second, it's interesting to us because there's been a lot of emphasis on what goes on with this estimator under interference. There's actually been not very much attention paid to what happens to this estimator. And one interesting thing to see is that this estimator also has problems with interference because it ignores all correlations. And obviously, outcomes are correlated between customers. So one of our things, that kind of mini problem that arose here, was to understand, does interference cause problems for us because this estimator is also biased? And what's the impact of that? So that was a thing that, as far as I could tell, hadn't really received much attention in the literature. Okay, and then the last step is decision making. So we use, in the same way that these are by far the most common things that are done in industry. When I say most common, by the way, obviously you may control for covariates, right? So there may be pre-treatment covariates, things like that. I'm obviously leaving all of that complexity out of here. I think one could easily start thinking about models that are more complicated from a regression controls perspective, but it's not changing the fundamental property that modeling the interference is not a thing that's usually done with the naive estimators. So what does the decision maker do? They form a t-test. That's, again, the most typical thing, or t-test statistic. They'll look at the DM estimator, difference in means estimator, divided by square root of the variance. And then the decision rule is something like, look at your test statistic and reject it if the magnitude is large enough. I mean, all of these pages could be taken out of, like, the first 3 pages of a stats book or something. Yeah.
Is there any general relation between bias in the difference in means estimate and any bias that's in the variance estimate?
That's a great, honestly, I was wondering that. I don't have an answer to that question. I think it's a super interesting question. I'm going to try to show you at least what we found. Part of that, I think one has to be a little bit careful there, because I'm going to split the problem, unsurprisingly, because I'm looking at hypothesis testing. I'll split it into false positive probability and power. So I'm going to sort of tell you different things in those 2 regimes. I don't know if there's sort of general results on bias in the non-null setting and the variance. We obtained some interesting, there's one thing that's not in the talk or the paper, which, again, I don't think this should be surprising, but I couldn't find it anywhere, which is that intuitively one should expect the covariance between successive customers is negative. Because if I book, then I've reduced inventory, so I should make you less likely to book. And it takes a little bit of work to show that, but that's, in fact, correct intuition. And then because the covariance is negative, one would think that maybe that would push forward into being able to say something about the way in which the variance estimator, the variance estimator is biased by missing correlations. The issue that we ran into is that that would be true in a world in which both systems are identical, so we leverage that for analyzing false positive probability. But if the 2 systems are different, that effect interacts with the treatment effect. And that we weren't able to come up with any nice expressions. So yeah, I don't have a good answer. But that covariance business that I just mentioned, none of that is in the talk or the paper. OK, so returning to the decision rule is always like reject if the test statistic is big. Now, what does big mean? The usually way we think about big is we fix a desired size, which is our false positive probability target. That might be like 5%. Then we do a lookup against a normal or a t-table, and we end up with a number, 1.96, and we reject if it's bigger than 1.96. Okay? So what's the net output of all of this? Like, what is the decision maker looking for? When we do these kinds of things, what the decision maker, if they really believe what's in the stats book, then what they think is happening is, if the truth is that the GTE is 0, then I should not reject the null, right? The null being the GTE is 0. And so if the truth is that the GTE is 0, then I want the chance that I reject to be controlled at alpha, which should be no more than alpha. If the truth is that the GTE is not 0, then I want that to be as high as possible. Okay, and that's these 2 statements. So basically the 2 informal goals, and I'll clarify why they're informal in a second. The 2 informal goals are that false positive probability is controlled at level alpha, and that your statistical power is as high as possible. It's basically hypothesis testing is binary classification, and these are the 2 goals that I have in binary classification. Why is it informal? It's informal actually because H0 not true and H0 true are not well-defined things to condition on. When H0 is true, right, what does that mean? The GTE is 0. In my setting, there's many systems that can give rise to the same booking rates, booking probabilities, that are different from each other. And without a distribution over those systems, like putting this to the right of the slash doesn't mean anything. So that's not a well-defined event. And more commonly, this is the case, certainly when looking at alternatives. This is standard, right? That if I look at power, I have to talk about power at a specific alternative, which I did not make precise here, right? So one of the things that I'm going to first focus on false positive probability and try to tell you a little bit, how do we tackle this composite null problem? So the composite null is the fact that H0 is this composite of many possible system pairs that give rise to a difference that's 0. Now, before I do that, I just want to say one thing and then pause a second for questions. This is a weird decision-making framework. I think we should all agree on that. It's like weird and like very commonplace at the same time, right? And this is a thing I was wondering working on this too. Like, I think there are 2 motivations for this kind of work. Either where you want to end up is you want to come up with a decision-making procedure that's so unambiguously better that everyone should stop what they're doing, like run and trash everything, all the code on their systems, and start over with what you just came up with. Or you're seeing something that everybody is doing. And the only question, the scientific question, is, what is the implication of what you're doing? In that world, I'm not spending a lot of time asking myself whether what they're doing makes sense. I'm really just trying to understand the implications of what they're doing. Because I got to be honest with you, I have a lot of trouble with sort of accepting, null hypothesis significance testing as the right way to make business decisions. But that's not my call. Like, a lot of people do this every day. So because a lot of people do it every day, as a matter of science, at least understanding what the implications are of what they're doing is worth it. I just want to make that clear to everybody, because I think a common reaction at this point would be, I just don't think that's the right way to do things. That's fine. But then we should run out and develop this alternative world-killing strategy that's way better than what they're doing right now. And we haven't been successful at that over 100 years of trying. So I think that's part of the problem in industry, I feel, is getting people to a place where they understand the consequences of the decision-making procedures they're using. So that's something I think I find very interesting. That's one of the reasons I got into this work, was that I think there's a lot there to be able to take, for example, one thing I would love to see more of is a more Bayesian perspective to decision-making, where past experiments inform allow you to form a prior before you run your next experiment. That would be a much more sensible way, in my view, of thinking about decision making, but that's not typical. It's not that it doesn't happen, and there's certainly large companies in particular, I think, that have done that, but this is still extremely commonplace. All right? Okay, let me pause there for a second. Questions on any of the setups so far? Okay, so birth-death chains for treatment and control. Experiment is a mixture of the two. I get some data out, and then I use the data to form the difference in means estimator, this variance estimator, run a t-test, and then use that to reject the null.
Why do you run a t-test? I mean, what guarantees of asymptotic?
Nothing guarantees.
Asymptotic behavior you have?
Yeah, nothing. That's the whole point of the talk, right? Is like they don't have that, but they do.
People do other things. I mean, just like bootstrap, resetting. There's a million of other things that one can do.
Yeah, it's interesting, actually. So Bootstrap is one that I was really surprised wasn't more commonly used. I think there's a couple of reasons. Most of them stupid, honestly, but they're important to highlight. So one of them is that these test results are typically populated into dashboards that are continuously accessible. And does it need to be that way? I don't know. That's a different question. But rerunning Bootstrap at scale for all the experiments that a company has running is something that experimentation platform teams typically aren't prioritizing against other sort of needs. So that's one reason that I bring up, is the fact that they're running these. And then that raises a whole host of other issues, because now you've got effectively sequential testing happening, right? Another one that I found somewhat surprising, I think may be interesting to some people in the room, but it isn't, certainly not part of this talk, is just the fact that there's every team that I've talked, virtually every team, I guess not all, but virtually every team I've talked to that builds experimentation platforms in companies is a cost center. They really only exist to serve other business units. They're not generating any revenue on their own. And that actually turns out to have some really important implications. I think the thing it's closest to is sort of the stuff that Stephen has thought about a little bit with principal agent hypothesis testing, where what ends up happening is that a lot of the statistical infrastructure they're building is in response to the demands of data scientists that have very strong incentives in play for what they're asking for. And that creates an odd sort of environment in which what gets built actually is the outcome of a game that we don't understand very well. And so I'm not going to say any more about that, right? To make sure I finish on time. But I do think that there's desiderata, maybe is the best way to say it. There's desiderata in the construction of the environment that go well beyond what we would do as methods people. But that said, as narrowly as a methods researcher, that question of what is going on with this choice is what motivated the talk. Yeah. Okay, so let me talk briefly about maybe the one big assumption that I'm going to make, and then what that gets me. And we'll see how I do on time. Hopefully I can get through most of this. Okay, so I already said this, that there's many potential treatments that can yield a GTE of 0. And so one thing that we do, I think this is maybe, I'm going to try to convince you that this class of treatments is interesting in its own right. And it has the property that if I know in advance that the treatment lies in this class, and I tell you the GT is 0, then it collapses the null to being a point null instead of a composite null. Now, monotonicity the phrase we use is monotonicity. Actually, in another talk, I got feedback that maybe that's not the right phrase to use, so I'm open to workshopping this. But what does monotonicity mean? It basically means that the treatment is monotone if the sign of the change of the booking rate is the same in every state. So roughly speaking, in words, what does this mean? That the sign of the change is not state dependent, averaged over customer types. So here's a case where, like, for example, some customer types may go up, some go down. I'm just saying that on average across customer types, in each state, the sign of that change is the same. There were similar things that were studied, some in an empirical context by Dave Holtz, and then others in sort of more methods papers. Here, we had an early definition like this in our paper from 22. One I'll call out here is this paper by folks from Lyft, where they were looking at shadow price adjustments to deal with interference. They do their analysis under an assumption like this one about the treatment. Okay. Now, there's many examples of treatments that could be modeled this way. It was funny because initially, like when we started working on this, it was just like a methodological interest to us. Like, what is an interesting assumption that gets to a point null? But then I realized, actually, most things that you do fall in that class. There's like some things we do that are genuinely state dependent, but many things are not. So increasing information, introducing new payment flows, changes to the user interface. The vast majority of these are really like state independent. If I think the sign of that is something, and there's no particular reason to think that depends on how many things I have available, or certainly not in a first order way. One of my favorite ones here, a key thing about all of these is that I also may not know in advance the sign of the effect. Okay, that's important. And so like one of my favorite ones about this is this Etsy one. Etsy offsets carbon emissions from shipping and packaging on this purchase. And that's one where certainly I think, like, depending on where you live in the country, that is like a pro or a con, that's what they're doing. So I think for us it was interesting to then see that there's a wide range of interventions that potentially could fall in this class. That said, I do want to say for the purposes of this talk, and it's a LIDS colloquium, that I think the interesting thing about that is that kind of what it gives us from the perspective of our model is a class of treatments that's plausible and interesting, and that has a property that really then makes analysis tractable and lets us say some interesting stuff. Okay, so I think it wouldn't be interesting to say what I'm about to tell you if it wasn't plausible, and it wouldn't be enough if it was plausible without any technical consequence. And of course, there's the classic box quote that's mandatory on any slide like this. All right, so what do we get out of monotonicity? We get that if the treatment is monotone, then if the GTE is 0, so if you have monotone treatment and the GTE is 0, then the booking rates have to be identical in the two systems. So this is what's sometimes known as the Fisher null, or the Fisher-Sharp null, that the data generation process under treatment and control is identical. Okay? And one thing I just want to point out for those of you that care about this sort of thing, one reason I found this project fun is that I learned something about birth-death chains that I didn't know before, which is really cool because they're like, again, like I said, one of the first Markov chain models you learn. So birth-death chains actually have a very nice property, which is called stochastic monotonicity, which is that if you initialize the chain in two distributions, one of which stochastically dominates the other, that property is preserved for all time. And continuous time analogs of birth-death chains exhibit the same behavior. This is a very nice, very interesting property. And it turns out for us that's ideal because if you combine that with monotonicity of booking probabilities, it sort of gives you exactly the machinery you need to get this type of result. Right? So that was kind of nice. Okay, so the first thing that I want to tell you is then what do we get as a consequence? And now I can look at false positive probability, but under this restriction of monotone treatment. Yeah.
So the assumption that the time it takes for let's say the booking to become reavailable.
That doesn't change with treatment.
Doesn't change with the treatment.
Yeah, so one of the reasons that that's the case in this paper is that we're looking at randomization on the customer side. And so it's hard to imagine sort of like how treatment on the customer side can then get fed through to changes in just those rates. It feels like I would need a much higher dimensional state representation where I'm tracking what type of customer booked me, and that's having an impact on my, and so yeah, I think one thing is that I believe that most of what I'm about to talk about is true even if you focus on listing randomization, where the listings are what's treated and allow that type of thing. But you would need a very different model. Like, so qualitatively, I believe it, but it's just a conjecture. Like, I don't have theory that fills that in. OK, so I'm going to keep one eye on the time here, and I just want to make sure I'm able to get through the results. But now that we've got all this set up, the results are a little bit quicker to present. So I think a simple way to think about what I want to tell you is I want to talk about false positive probability and power. And I'm looking at a test statistic that involves a difference in means estimator and a variance estimator. And so one way to think about that is I care about these two quantities under the null and in a non-null setting. So that's kind of what I'm going to try to tell you. Okay? Now, under the null, it's pretty obvious to see that the difference in means estimator has mean 0. So that's not that the two systems are identical, so that's easy. What surprised us is actually the variance estimator is unbiased for the true variance of the difference in means estimator. And remember, that should be surprising even under the null where the two systems are identical, at least to us it was, because there's no correlation included in the difference in means estimator, in the variance estimator. And the proof of it also is a little fun and cute because it combines ideas from Fisher and Neyman, which, like, for those of you that know, didn't get along. And so it was nice to actually like figure out a way to like combine sort of some of the statistical ideas from each of them. And the rough idea is that we prove this result actually in a great deal of generality. It's sort of for arbitrary dependent observations. This is true. And the trick involves first applying a random permutation to the data, which converts your arbitrary dependent observations into exchangeable observations. And what's key is that if you're under the Fisher null can be restated as treatment is independent of the data generation. And so if that's the case and you apply this random permutation, you haven't changed the distribution of the test statistics. So effectively, I can assume without loss of generality that my data is exchangeable. And once I do that, Neyman has this paper from 1923 where he proves a variance decomposition under an assumption of constant causal effect or constant treatment effect at the unit level. And we can use kind of a variant of that algebra, elementary algebra, to basically get this unbiasedness of the variance estimator. So it's like, we looked for a while to see if this exact result was in the literature, and to the best of what we could tell, it's not there yet, because again, it combines kind of two odd sets of ideas together. Usually this exchangeability arises in the context of permutation testing or randomization inference. And Neyman's sort of variance decomposition shows up in sort of different places. So anyway, I'd love to hear from anyone if you've got references to sort of related things that we should look at. But that's kind of the key output, is the variance estimator is unbiased. Now, if the variance estimator is unbiased, the difference in means estimator is unbiased. One should expect that, in fact, like false positive probability behaves well. And indeed, that's exactly what happens. This I won't belabor. But basically, we show that asymptotically, the test statistic is normal under the null. And this is really nice, because one of the things it's telling you is that you don't have to worry about the inflation of false positive probability. So the intuition we got from the toy example at the beginning, now we should be leaning into more. Because if false positive probability is controlled, and I'm telling you the treatment effect is overestimated, I'm feeling pretty good about myself. And the only thing that could break things now is if the variance is poor. And so we'll talk about that. Just one note here. One thing, again, that I couldn't find in the literature is that there's sort of an interesting thing going on here is that we have Markovian data, and we're analyzing a central limit theorem for the difference in means estimator, and I couldn't find that result either, because central limit theorem for the difference in means estimator. It was interesting talking to Stefan, actually. He just finished a very nice causal inference book, Stefan Wager. And in the beginning of that book, there's a proof of the CLT for the difference in means estimator under IID data. But even he had trouble finding that proof. It's not, the proof isn't hard. It uses elementary techniques. But it's just surprising, I think, some of these like basic instruments are things that are not available in textbook form. Which is mostly an add that Stefan's causal inference book is amazing. So you should definitely look at that if you haven't already. All right? So that's false positive probability. Let me talk about power. Now, I've kind of already given you a hint of this type of result, that the treatment effect is overestimated when we have, and the generalization of the toy example at the beginning is under monotone treatment. So if the treatment's monotone in this way I described, then you indeed get this result that the treatment effect is upward biased. The estimate is upward biased. One thing I guess that I'll just say here is that that type of result, there's some similar things in mean field settings. What's nice for us is that we can use that same stochastic monotonicity to prove this in finite samples, that you get finite sample bias. And exactly for the intuitive reason that I described, treatment is overestimated and control is underestimated. I'm glossing over some things that I think are important technically, but not in the talk, which is it matters what the initial distribution is, for example. So you have to initialize, if you think about the distributions as living in this lattice determined by first order stochastic dominance, you have to initialize it a distribution that's between the treatment and control steady state distributions. So you can't sort of arbitrarily prove such a thing, but we thought for the paper, I think what we put in is an assumption that the initial distribution is the control steady state distribution, sort of imagining you start from control and run the experiment or something. Okay, so that leaves just the variance. And so what I've shown you so far is that the treatment effect is being overestimated. Now, overestimated relative to what? Relative to the truth. So one way to think about that is if I had an unbiased estimator, then the numerator of a t-test statistic using the difference in means estimator is larger on average than the numerator of an unbiased estimator. Okay, so that's sort of that first statement. Now I've got the variance is this naive variance estimator that I wrote down. What variance do I want to compare against if I want to look at an unbiased estimation strategy? Well, one thing we imagine is, like, suppose the decision maker alternatively had access to an unbiased estimator and had access to the correct variance for that unbiased estimator. Okay, so then what we imagine then is they could form a different test statistic and use that instead. And I think for us, sort of like all signs were pointing in the direction this has to be terrible, and indeed it is. And the question was just how do you get there? And that was when we came across this paper by Vivek, the first paper. And in that paper, one of the things they do is they prove a Cramér-Rao lower bound, which is actually interesting to me. I had a paper from NeurIPS a couple years before that had a non-parametric maximum likelihood estimator for Markov chain experiments that actually exactly matches the Cramér-Rao lower bound, which makes sense. Like that should have been the Cramér-Rao sort of variance achieving estimator. So what they do is they basically say, okay, in the worst case, like we can construct an example of a birth-death chain where unbiased estimation has the property that the variance will blow up exponentially in the size of the state space. So if you look, they essentially construct a sequence of birth-death chains which have the property that if you had an unbiased estimator, then the variance of that estimator is going to blow up exponentially in the size of the state space. But their system is sort of tailor-made to get that behavior. And unfortunately, one of the things that one needs to note is that there also exist examples of systems with larger and larger state space where that doesn't happen. And so for us, like what we wanted to show is that that's a generic phenomenon. And so what we do in the paper is that we consider any sequence of systems, essentially, pairs of control and treatment systems, with the sort of systems approaching a mean field limit as the size of the state space goes to infinity. What do I mean by mean field limit? Informally, the way you could think about this is that if I have the size of the state space going to infinity, then what I'm asking is that the booking probability curves and the death rate curves approach an appropriate limit, approach functional limits as the state space grows to infinity. So that seemed like a pretty benign assumption, and from our perspective, that feels like a pretty generic result, that the exponential growth of the variance is unavoidable. I also want to say, like, that exponential growth, and by the way, it's not hard to see this, but because the booking outcomes are binary, the naive variance estimator is clearly bounded by a constant. And so you have this like exponential gap in the variance, and the numerator is overestimated. So one would expect, yes, that, like, your power is much better using the naive strategy over any unbiased strategy. So let me just first show you, this is like one curve. I'm actually not going to spend a lot of time on this graph. This is one example of like particular parameters where the power, this is the log of the false negative probability. So false negative probability is 1 minus power. So you want this to be small. And you can see like the gap is enormous already, even in this example at like k equals 70. Now our treatment effect here was like 0.02 in the booking probability. I think putting all that aside, it's an extreme result. Like this exponential growth with the size of the state space says it's just sort of so good It almost wouldn't have mattered, actually, if you were overestimating the treatment effect. So I want to be clear what the main takeaway is here. The main thing we're trying to say is that relative to being unbiased, you're overestimating the numerator, and you have a massive gap in the denominator in your favor. That's probably not what you would do if you were debiasing. If you were debiasing, what you would try to do is remove some bias. But like most things you would do that will introduce some variance. And so like one example of this is the DQ estimator from Vivek. That's a much more plausible thing to do than to be fully unbiased. And that has a pretty favorable bias variance behavior, relatively speaking, if your interest really was in debiasing. But even that has the property that the naive variance the naive treatment effect estimate will be larger, and the variance will be smaller, right? So sort of like, I think what I'm trying to say is this is the most extreme case of the bias variance trade-off, and both the numerator and the denominator are working in your favor if you're using the naive sort of test statistic in increasing your power, right? So what are the takeaways? Like if the treatments are monotone and the decision maker uses a naive test, your false positive probability is controlled correctly, and your statistical power is like much higher than it would be with any unbiased approach. So this is what I meant at the beginning of the talk when I said you're strictly better off not debiasing. Just to drive home again, reducing bias tends to increase variance, not always. It's a bias variance decomposition, not a trade-off. So maybe you do something that actually gets you both, but in general, this would be the case for most of the proposals in the literature. And so most low bias estimators probably still are going to fall on the wrong side of this boundary. So I don't think that, my point is, I don't think that's the right way to think about how am I going to do better. Like somehow I'm going to evade this by coming up with a slightly lower bias estimator that actually gives me good enough variance and I'm better off. I don't think that's the right way. I think the right way is to focus on monotonicity. Like what's the role of monotonicity? Okay? And here it's important to know that if you get outside the monotone world, things can be arbitrarily bad. Okay? So in particular, and getting outside the monotone world is also not that hard, because you could imagine something like I choose to do this like price intervention, where whether I raise or lower prices depends on how much inventory is available. So maybe when there's not a lot of inventory available, I'm going to raise prices. When there's a lot available, I'll lower prices. Now that's clearly state dependent. And using interventions like that in the paper, we show that in the absolute worst case, in fact, there are treatments where the true GTE is 0, but your false positive probability approaches 1, and that's basically because of the bias and the difference in means estimator. There's also treatments where the true GTE is non-zero, but your false positive, your power, stays very low. And that's essentially because your naive estimator maintains a GTE that's an estimate that's around 0. So your power never really grows. Okay? So things can be arbitrarily bad, which obviously prompts the question, sort of how state dependent is my treatment? And that's the sense in which I was saying earlier. I think a key takeaway from the work for me is, as you're thinking, as a platform thinks about the value of debiasing, a lot of that comes down to the extent to which you think this type of state dependence is really a primary driver of the treatment effect. And that would be at least one reason that the takeaways in this talk are not the right ones for a platform. A couple of quick comments on modifications. I won't say a lot about this. If listings are heterogeneous, the stochastic monotonicity properties of birth-death chains no longer apply. So you need, and basically the issue there is that you need some substitution pattern across different types of listings in that case. You have a multi-dimensional queuing system. And so for that, we sort of rely on a multinomial logit choice model that we introduced in an earlier paper in 22, and look at an appropriate definition of monotonicity in the mean field limit, then sort of we're able to get some related results to what I've already shown you in the talk in that setting. And so our conjecture is that we end up with sort of a similar power result, and we're able to show that one does actually have correct control of false positive probability in that setting. This is a simulation that kind of demonstrates similar behavior in that setting. Another interesting thing is that we can accommodate some types of non-stationarity, and that's because the stochastic monotonicity of a birth-death chain holds at every time point. So the birth-death chain itself could have some variation in the parameters over time, but you still have stochastic monotonicity. So there's like an easy ability to incorporate some non-stationarity into the result But you have to be careful about what the estimand is there. So the estimand of interest, or that you can say something about there, is the in-sample estimand, the estimand during the time horizon of the experiment. All right, and then finally, what about other goals? So, I think it's clear that this isn't sort of all that goes on in decision making. And I think like the two big things I'll highlight, one of them is that often when we're making a choice to launch or not launch something, we're also thinking implicitly about the cost of that thing, or maybe even explicitly. Which means then we really care about the treatment effect estimate. Then it's not the case that you're just seeing is it different from 0, because if you're looking at it above C, then you've got to think about what's the cost, what's the treatment effect relative to the cost. And then the other one I think is that there are other metrics of interest which don't obey this inflation effect. The one that's I think primary in a lot of work that we've done is thinking about profit or revenue. When you change prices up, demand moves down. And because of that effect, it's possible that you get the sign wrong because of this same kind of interference phenomenon. And so when you're getting the sign wrong, now you can't rely on the same types of claims I'm making in this talk. So I think that's another case where the decision-making framework has other issues, but it won't fall in the class of what I've talked about. So I think to summarize, sort of our takeaway is one that to anyone who takes the whole pipeline view or the statistical decision theory view of statistics isn't surprising, which is that you should start by being clear about what your goals are, and then use the goals and your knowledge of the intervention to inform exactly what you do. And I think it is sort of useful at least to sit back. Maybe one of the things for me that came out of this was that blindly thinking about correcting interference is not the right thing. You really want interference correction to be a targeted methodological goal that focuses on the sort of nature of the intervention and the desired sort of decision-making goal to motivate why you're doing that, right? And that hasn't been something that I certainly prioritized up until doing this work. So hopefully kind of the takeaways make sense. If there's any questions, I'm happy to take them. I know it's already 5. So let me stop there.